Good afternoon to anyone, or good morning, or good night. I don't know, depending on where you are. I'm very happy to be here, and again, thank you for inviting me. I've been already presented, so there is no reason to add and to enter into detail about myself. As a background, I'm a geologist and at present a lecturer at the Earth Science Department of the University of Rome. In addition to what has been already said, I'm strongly involved on transportation asset management, but as a professional and research point of view, and I'm a member of the Transportation Research Board in the United States as well, and the PIRC, the World Road Association, in the engineering, geology, and earthworks sections. I'm also, since 10 years, one of the co-founders of Nazca, and I'm CEO since more than 10 years right now. Nazca is a limited company, spin-off of the University of Rome, that over the years became an international leader in the analysis and monitoring solution for the management and control of infrastructures and natural hazards. We started in 2010, being incubated by the European Space Agency, and right now we have also a lot of projects with the European Space Agency. Nazca is done of some 30 professional researchers and academics, most of them qualified and expert on geological hazards and remote sensing. The core technologies are on satellite, terrestrial, aerial, radar, and photomonitoring and laser. So that's the main focus. At present, we are serving more than 400 customers from 30 countries, and looking mainly and using mainly this kind of technologies. Today we will talk mainly about photomonitoring. Is one of the last news. It's a probably less common technology than, for example, INSAR, that over the last years is becoming quite popular, fortunately, as it has really a lot of potential. And we work as Nazca in several sectors, from civil protection and asset management for transportation, hydropower, oil and gas, and mining. I think it's time to start entering into much more detail on the topic of the presentation today, and starting with this matter. Just to give you an idea, some statistics say that in 2020 there was such a number, a so huge number, so trillions of pictures taken, considering all the people around the world and all the sensors existing. So this is really a huge number, and about 90% of these were done by smartphone. I put this picture on the top right just because this was my first digital camera that I remember I bought with my first salary. It was some 20 years ago, more or less, a little bit more. And I remember it was 1,000 euros. It was 2 megapixels and 3 per zoom, optical zoom. If you look at what is available today, this is quite impressive to see how this technology has been grown over time. And today we have very, very high resolution cameras in our smartphones like these ones, but there are plenty of opportunities. And so that's the starting point. And I think that the availability of images is so large that for sure, also in our field, we have to try to take advantage of this kind of pictures. This is also expected to grow so much, and add another point of view, as UAV and drones are becoming a very, very huge market. You can see since 2014 up to 2025, what is expected to be the growth of this market. Of course, the growth of this market means that there will be more and more drones flying around, and also the regulations are becoming a little bit less strict along this line. And so you can imagine how the number of images available will be in a few years from now. At the same time, at present, there are more than 600 satellites orbiting around the Earth, only only for Earth observation. So looking at our planet and try to use data and images collected to infer some information. And so 600 satellites is something very large, but now they're growing with a number of 100 per year, even more. So this number is expected to have something similar to the growth we have seen for UAV system. So combining ground-based smartphones, UAV, satellites, the amount of pictures, of images that are available, and even more that will be available in the future, is impressive. And especially if you look at their features, there is a potential to use these images to catch information in our field. Today, we will focus mainly on landslides and geological hazards, but still today, images are used for everything. You can see here from medicine, agriculture, astronomy. Astronomy is made only by pictures, video surveillance, military, and so on. So this is a good point, and the reason because it is a good point is that our world, so geology or natural hazards, can take a lot of advantage of the potential of technology and the growth of technologies that is not just done for ourselves, but is done for any field, any economic field. So there is a lot of investment, of course, in this area. So at this point, I want to start with what is photo monitoring. Images are taken, you have a picture, but if you take another image a few minutes later, like I'm showing here in a very simple experiment done in the office, you can see that there are some differences. You can easily recognize this difference. I think that all of you are able to see that there are some things that are almost stable. Can see that the pictures are not taken exactly from the same position, but there are a couple of objects that are no more present, so that are changing and disappearing. That is a apple and a yellow pen, and at the same time, there is another object that is moving, is shifting. So when we talk about something that is no more present, we're talking about what is commonly said change detection. When we are looking at something that is moving, this is displacement detection. So what we are doing and what you are doing with your eyes is to see what is the change and what is the displacement. And this is the same thing that can be seen in this slide. What you see in this slide, you see that there are some patterns that are changing. There is some blue and some red. But what is the grid? The grid is no more than the matrix, because any image is done by a matrix, and this matrix is done for any one of these pixel, there is a value. In this case, the value is the color. The color is just a combination of different matrices, as you know, but can be also a single matrix. And that's it, what you can see. You can see that some objects are changing in size, are moving, keeping the same size, and so on. The first part is change detection. Change detection is identification of changing features, new features, disappearing features, and so on. Displacement detection is identification and monitoring of features translation, rotation, and shifts. This is exactly what, in our view, is photo monitoring. Photo monitoring for the change detection part is quite simple to be understood. You just take the first picture, of course, the basic mathematical matrix. You change with the other, we make a difference, one minus the other, and you see the difference. And that's exactly what you can see between the two images that are shifting on the left. The difference, so the differential between the two in terms of values of pixels of radiometric response is on the right. Of course, you see that there are a lot of changes, but most of these changes are caused by a change of brightness, noise, for example, the sun, some special feature of the camera, and so on. The good point of this method is that it's very simple. It's just, for the mathematical point of view, is very simple and very fast, of course. But what you see on the right probably is not exactly what you're interested in. Of course, when you start to work with more advanced solution for change detection, this is just an example of the type of algorithms. There's one category that is called structure similarity index that is analyzing not just the radiometric response, but also the brightness, the contrast, structural elements. So a little bit more advanced algorithms. You can see what is the difference. So exactly what is the change of brightness and so on is not considered, is neglected, it's filtered. And what is resulting is only, you see in red, and then in this green polygon on the right, the area where something has changed. Of course, it's much more better in terms of computation, but it's much more slow. And this is a key point we will return later. At the same time, taking two metrics and looking at an object, you can track what is the movement. Look at here, you have these yellow pixels, 4 yellow pixels, sorry, 5. As soon as they have changed in the second pictures taken at different times in this different position, the red arrow, the red line with the arrow is just showing you how many pixels has changed. So you can count 1, 2, 3, 4, 5 pixels. So it's change of 5 pixels in just one direction. That is the X direction. At the same time, you can see if something is moving in the Y direction. And this is what you can see here. And you can see with the module and the length of this red line, the direction of movement. So this is, in a few words, the basic principle of displacement detection. However, we must take care that the displacement with this technology can be identified in the plane in 2 directions, in the plane normal to the line of sight. So if you are normal to the object that is moving, like in this case, you will see that the real movement is exactly the number of pixels that you identify. If you are not perpendicular, you see just a component of the real deformation. And in order to derive what is the right number of pixels, and if you know the size of the pixel, to derive the centimetric or millimetric deformation, you need to know what is the geometry and the inclination of your surface with respect to the line of sight. That said, let's start a little bit more on how this works. Displacement detection usually is looking at feature. There are different algorithms that we use for this technology that are implemented, that are based on feature tracking. So you identify the feature. You can, for example, see the nose of this man is clearly recognized in the upper picture on the right, on the man on the right in a similar picture taken in another moment, but also taken from a different position, so it's rotated. But you recognize the same picture. You connect a lot of these features, and you're able to recombine these images and to see at the end if there are differences. But you can use cross-correlation, and we can use also more advanced technologies like optical flows. The incredible point of this technology, however, is that we are not only able to measure the number of pixels. I was telling you before, to simplify, you can see how many pixels the object is changed in space. Apparently, it's very simple. What probably is a little bit less simple to understand, and also is definitely less simple to do, is to measure displacement that are below the pixel size. With this technology, there is a potential to reach 1/100 pixels, so 0.01 pixel displacement. So this means that if you have a pixel resolution of 1 centimeter, you could be able to measure 0.1 millimeter. If you have a pixel resolution of 10 centimeters, you could be able to measure 1 millimeter of displacement. How to do this is a little bit complicated to understand, but it's just a matter of physics and math combined. And so the sub-pixel displacement detection is something that is feasible with this technology. Of course, I'm not surprised if some of you that is not familiar with this technology is not trusting me, is considering that I'm saying not reasonable things. In order to convince you, I will show a couple of slides derived from an experiment that was done recently, combining the results of displacement in a calibrated lab in Austria at the Graz University, and combining also a total station and this kind of camera on the left that you know very, most of you have seen probably in the markets, is a standard Nikon D3200 model. This is just a few specs about the camera and also the camera installed on the total station. And this is the setup of the experiment. This is a very environmental controlled. There is no change of light, no change of humidity, and there are control systems that are able to set movement with a precision of 2 microns. So there are some systems in this lab that allow you to impose and to set some displacement with a precision of 2 microns. So that's what we have done here. We have set the camera, so the sensors, and then the total station in the same position at about 30-meter distance, up to 26.3. From 6.3 to 26.3 is the maximum distance that can be achieved in this lab. We set some displacement incrementally, and then we measured and we did this analysis to have a confirmation. I think that you are looking at something that is moving. Can you see this? Probably not. As when I was showing you some basic examples, you are able to see the shift from this clear object and few pixels from one point to another, if you remember my first slides. If I'm show here what is, I'm shifting. If you look at here, you see that are changing images, what is called master and slave, even if slave is no more a word that can be used, it has been already changed. But yeah, I'm shifting, but probably you are not seeing anything on the map, visually with your eyes. But what about the tool? What about the software that is using this kind of technology? This is what is able to see. Is able to identify that all the area is green, so no movement, 0 pixel. While there is all these systems, that is the machine that is controlling the deformation, that moved of an amount of 0.4 pixels. It was about 1.2 millimeters at a distance of 26 meters with a camera that is a very standard consumer camera. These are some additional information about the precision that can be achieved. Of course, this is true in theory, this is true in the lab, but what's happened when you go in the real world, a lot of issues. Images, for example, from satellite are not perfectly co-registered, so they are not taken during the orbit exactly from the same position. So you see that are shift a little bit, so different point of view. You see that the light can change, as you can see here. There is a shadow, there is a changing of light due to the sun. And not only to the sun, there should be fog, low visibility, and so on. You can have the rain that in sometimes can create some issue to your lenses. And of course, you can be in areas where the object in front of you is quickly changing. And this is exactly where, over the last years, we focused our attention. So try to bring what is feasible in the lab, and is also done already in some fields, into the real world, into a geological world or a civil engineering world. So it's to use a tool that is able to solve all the issues that you can see in this picture. This tool that we developed over our research time of some 8 years right now and 3 years of development is called IRIS software. That is a software for change detection and displacement analysis. What's the feature of IRIS? IRIS is able to make some pre-processing, co-registration, change detection, displacement. And what is interesting and quite original is that in addition to all these features, is able to analyze not just one image to the other one, but to analyze a set of images, a huge set of images altogether, so that to increase statistically quite a lot the quality of the measurement. And what is good Even more is that this software is able also to process data automatically. So let's imagine that you have a camera or a webcam that is collecting images every certain times, or also satellites that are collecting images with a certain rate. You can automatically allow the software to process the data and to provide you what are the changes and the deformation. What are the main application? Landslides displacement is for sure a good application for this tool, but we had a lot of interesting examples for glaciers, from earthquakes, flood mapping, water level monitoring in reservoirs, and of course, structural monitoring, and so on. And I will show you some examples. What are the possible data? Which kind of sensors can collect data that can be processed in IRIS? IRIS at present is technology and platform agnostic. So it's able to process data potentially from any sensor that has been used, any wavelength, and any platform. You can collect data from a smartphone, a consumer camera, an industrial camera, a webcam, a satellite, a UAV, an aerial, and so on. And also can process data in the optical wavelength, but also in infrared, thermal infrared, and radar. And I think right now it's nice to start exactly with a radar image, just to show you that it's not only necessary to use optical images, but any image that is done by a matrix can be used for make change. This is an example of a radar image collected before and after a landslides. I'm pretty sure that in this case, differently from what I was showing you in the lab, you can see the change and the difference. Qualitatively, all of you is able to say, oh, it's moved along a certain direction. But what is nice is that with IRIS, it's possible to build a field map of deformation. And you can see here, which is the direction with the arrows and with the color, and also the length of the arrows and the lines is showing what is the amount. So you can see that this landslides is moving with a growing deformation from this part to this area, where it's changing a little bit, adapting to the morphology, the direction of the movement. So that's a kind of results that can be achieved combined 3x3 images from Cosmos SkyMed radar images. But of course, what we can use here, and this is even more fancy, is the results that can be achieved with images from PlanetScope. PlanetScope is a mission from the company Planet, satellite mission collecting optical images at 3x3 meter resolution with almost daily sampling frequency. And as you have seen here, this is a video showing, you can see the dates and the timing here, the growing and the changing of deformation over times in terms of meters. You see that in some areas you have deformation up to 50 meters in this area. And you can clearly identify where and how this is deforming between November 2017 and August 2019. And at the end, what you have, if you want to look just to a single final displacement map, that's the result. In color, you see the deformation magnitude, and with the white arrows, you see the direction of movement. But what is good is that this analysis has not been done just comparing two images. There are several images, some 60 images collected over time, between 2017 and 2019. And so for each one of these points, you have not just the final value, but you have a time series of deformation that is able to tell you how much and when and with which trend this deformation occurred. A similar application has been done in interesting landslides in rattlesnake, and this is a curious example because we were able to map exactly what was the field of deformation just with 3x3 optical images from PlanetScope, while on the contrary, satellite INSAR, for example, was not able to detect this deformation just because the movement was too fast. Probably all of you already know that satellite INSAR have some limitation due to phase ambiguity on the deformation of high-speed object, while this technology has no limitation in terms of size of deformation, especially if you are using the right algorithms for data processing. And this is a time series again that was done using what is called a multi-stack approach. So you're using a stacking approach using several images and combining all these images all together so that to have a statistically strong result. But again, as I was telling you before, you can just use a couple of images if you have just 2 images. And if you have no better than Landsat, so 15 by 15 meter resolution, you can use these images, and probably also in this case, you can just see the change, but you cannot see the movement. The software is able to see the movement, and that's exactly the amount of movement in meters again of this glacier. This is the Ring Glacier. It's considered one of the most deformable, one of the most fast deforming glaciers in the world. Okay, let's come back to the ground and to use other kind of data sets. In this slide, what you can see is just the time lapse of, you can see again, this is the time lapse of a webcam installed here, not for monitoring, but just for visual detection, qualitative visual detection. That this is what it's showing. And why this is what's moving, if you look at the same frames and we processed with iris, this is what can be achieved. And of course, if you have the distance, the features of the camera, you can have information about the deformation in metric value. But it's not enough, because you could be interested to have a time series, and again, as you have several time frames, you can have for each pixels a time series, but even more, you can also have an area and having what is the average deformation and the time series of deformation in this area. An interesting application that was done in the southern part of Italy, in the central part of Italy recently, not far from Rome, was a consequence of this landslides. It was not a very huge one, but so it's one of those landslides where high costly monitoring systems are not allowed, the cost benefit is not reasonable. At the same time, it was quite an issue because this road, this is a local road, but it was the only one connected a small 30 people village with the main city. Was blocked, so there was no other alternative. So it was quite relevant, even if the landslides was not quite relevant and in terms of size. So what the local authorities decided was to remove as soon as possible this material, but at the end, the slope were in this condition. And there was some timing to make intervention. So at that time, they decided to use a ground-based radar monitoring system that probably have been already explained in this seminar series. And yeah, for 3 months, the radar was there monitoring 24/7 with a very high precision the deformation of these landslides. After 3 months, unfortunately, the repairing works were not already done. And the asset managers of this road said, okay, we want to continue, but we have no more money. So we have really a few amounts of money that can be a couple of months of monitoring, and probably we need at least 6 months. So how we can do? Our answers was, of course, this kind of tool is very costly. You cannot do 6 months, so we cannot. If you want, we can leave here just this camera that we installed there, not for monitoring purpose at the beginning, just to see what was the change over there to better interpret the radar data. We left the camera there, and from this point, we did 9 months of monitoring just using these pictures. You can see the differences? Yeah, you can. Probably you can see that there was some change also over here. But what you can see even better is this one. We are able to detect any single small piece of rock that was before or was coming down, but also small deformation. Okay, as I was telling you before, the quality of the system is based on the size of the pixel. So as far you are, as lower is the quality of your sensor, and as lower is the precision and the quality of the mapping. But a good point, again, is that you can use any sensor that you want, and also you can use some systems like this one. This is a gigapan apparatus. So it's a mechanical system, robotic system that is allowing cameras to collect with a very high zoom, so a very high pixel detail, but at the same time moving the camera with a robotic system, and so collecting a wide areas view with a very high detail. Let me show an example. This is apparently a normal picture covering all this vertical cliff. But if you go a little bit more in detail, what you can do, and you can start to zoom in. You have at 800-meter distance, and you can zoom in, zoom in, zoom in. Normally, when you zoom in standard pictures, you have a strong reduction of the quality. But here, you can arrive at this level. So you have this level of detail in terms of few centimeter size. So you are looking really small piece. We have done a test a few years ago with this technology, a couple of years ago, and this rock cliff with multi-temporal images collected by this gigapan, and we were able to detect in 3 days 75 rock falls from these very small ones. Sorry, not 75, 84. A small piece of rock coming down. We are able to identify that some piece of rock were depositing here, and so on. So the potential of what we have done in 3 days, so identifying the areas where there was more activity, is incredible if you consider it was just a comparison of a couple of pictures taken by this robotic system. And what we are looking were also small piece of rock, like this one's, few centimeter size. We are able to detect that this one, before collapsing, tilted. There was a first tilting after 1 hour, and the morning after, it was fell, definitely. So this is the potential of this technology. At the same time, you can use really everything, and what you can use in some cases is also UAV. UAV can be used in 2 different ways. You can use a hill shade taken from a digital surface model. You see, in this case, these are 3 different hill shades collected at different times. And using these hill shades with iris, you can see what is the deformation over time. But you can use also orthophoto from UAV. In this case, we had some orthophotos, ortho images at 0.15 meter, so 15 centimeter resolution, and we are able to detect the movement over time of this area. You see here also the time series. We have few images, but you can able to see also if there are some trends and so on. Of course, in the same landslides, we used also a PlanetScope, and with PlanetScope, we were able also to detect some good information, like in this case, even if, of course, less detailed because the resolution is 3 meters. I was showing you before a very long-range system with a high-quality camera in the rockfall detection example. But what I'm showing here is something different. Probably you know, or probably not, at least not for not Italian, but for the Expo in Dubai, there has been done a 3D reconstruction of this famous statue that is in Florence, you know, and it was been built and printed and 3D printed in the world size, and is now at the center of the stand and the area at the Expo for Italy. During this action, there was this object where the laser scanning was installed that were moved, and while there was moving, there was some vibration. So the request, very challenging, was, are you able to detect the vibration of this sort of tripod in a way? And we said, okay, we can try. We set a mobile phone just in front of these systems, installed on a tripod at a few meter distance, and we start to collect a video, a high frame rate video. That's the result. We were able to detect the vibration. You see here the oscillation that, of course, are damping at a certain time with a 0.01 precision, more or less, identifying that there was a vibration of 0. With a maximum amplitude of 0.1 pixels. That in this case was on the order of few decimal millimeters. And this is to give you an idea also of the potential of not just images, but video itself. And all this done with a simple mobile phone. So I think that this final example, more than others, even if it's not related to landslides, it is the topic of this talk today, is giving the impression of the potential of this technology. And so just to, there are satellite drones. When you need something in real time continuously, as we are talking about early warning, probably you need a system that is permanently installed in this case. And over the years, we developed different systems. The last one is this one, what we call NetScam. So there are systems exactly built, specifically built to make monitoring. I finished. I take the chance to remind you, as already mentioned in the introduction, that for the first time this year, this monitoring technology, so photomonitoring, will be also one of the topics covered during the international course on geotechnical and structural monitoring that is done by a main course, 3 days, 4 hours per day, will be fully remote, completely online, with exception with the field trip, and will be over 6 months from June to December, master classes. Master classes covering different topics for any kind of monitoring system, from remote sensing to inclinometers and piezometers and anything else. You can find the full schedule at this link. And as we're joking at the beginning with the organizer of this event, if this is the worst or the best year to attend, usually this course was done in presence over the last 6 years. But for the first time will be online. This is a limitation because the relationship with people is limited, as is limited for any other field in the last year. But a good point is that can be easily followed by anyone all over the world at their desk. So that's potentially for someone that has problem to travel a good opportunity. And again, more information can be found here. And I finished. So thank you very much.